Welcome everyone to the Autoware and Precise Center Safe Autonomy seminar series. It's my great pleasure to have Professor Junfeng Zhao with us today from the Arizona State University. He's a tenure track assistant professor there, but he actually comes with a lot of experience working in the automotive and autonomous vehicle safety, and he spent over 6 years in General Motors R&D, and his interests are, in connected autonomous vehicles, the simulation and system integration, motion planning, electrified propulsion systems and controls, and of course, intelligent transportation. Professor Zhao today will talk to us about testing of these, autonomous driving systems. How do we get that level of assurance that we need to go to the next level from research to deployment? Welcome, Junfeng. We are very excited to hear your talk today.
Yeah, thank you so much, Rahul, for the nice introduction, nice words. Today I'm going to talk about my experience from both industry and academia in terms of testing and evaluating automated driving system for safety and efficiency, and hope to learn from other members from the community as well. So a little bit background about myself. So I got my PhD degree from the Ohio State University. We have a Center for Automotive Research over there, a lot of activities going on. And then I joined GM R&D, like Rahul mentioned, for 6 years. It's quite a long time period, actually, for my career. So over there, I worked on several projects. One of the major ones is serving as a technical lead of the InfoRich project. So the focus of that one was to develop the energy efficient connected and automated vehicle. So that project was sponsored by DOE, ARPA-E, and I had a great pleasure to collaborate with Professor Raj Kumar from Carnegie Mellon University and Jeff Gonder from Unreal. So I didn't realize that me and Rahul have this kind of overlapping because Professor Raj Kumar was a wonderful collaborator and also a great mentor to me. I'm glad to have that opportunity. So I'll talk about that project a little bit. Then in 2022, I came back to academia. I joined ASU as a assistant professor. I'm also affiliated with the robotics and autonomous system program and also clean energy system. So over here, I launched our research lab called Battery Electric and Intelligent Vehicle Lab. I call it the Belief. Kind of hopefully it's easier to remember. So today I'm going to talk about mainly two projects, okay, relevant to testing and evaluating autonomous driving system. It also reflects a little bit the transition of my career. So you can see the first project, as I mentioned, was looking to energy efficient connected and automated vehicles. Okay, that happened between 2017 and 2021. Back then, we had this very high expectation, high hope that very soon the connected and automated vehicles will be everywhere, right? And other than the safety, we have to explore other aspects to see how it can best benefit the society, right? A little bit too optimistic, but there's a lot of good learning and findings from that project. And I truly believe that maybe in the future, we'll revisit that topic once the technology is more mature. And starting from last year, we had a new project on the automated vehicle test and evaluation process mission. The focus slightly shifted, it goes back to the core topic, the safety, okay? So we work with local state government agency to develop a framework. That's the second part of today's presentation. Okay. Now let's look at the first part. So in 2017, ARPA launched this Next Car program, like I mentioned, mainly to explore the energy saving potential for connected and automated vehicles. Okay, because we'll have the onboard sensors, we'll have connectivity, then we can have better preview of what's going to happen in the traffic scenario, right? How do we leverage that and combine with the vehicle dynamics and powertrain control and improve not just the vehicle itself, right? Also imagine that we consider the transportation as a whole. How do we improve the efficiency? Okay. The goal was quite ambitious. The overall program goal was to reduce the energy consumption by more than 20% for CAVs under real-world driving scenarios. Okay. One thing is 20% is a keyword. The other one is has to be proven that it works in the real-world driving scenarios. I think that during that project, those two are kind of two challenging key points. Okay. So back then, there are in total 11 teams participating. So across different powertrain types, light duty, medium duty, heavy duty vehicles. GM, actually, our team, it was the only kind of an industry-led team participating. So we focus on back then, focus on the light duty vehicle. Okay. So, so this is our test vehicle. We took the 2018 Cadillac CT6. That was the first generation of vehicle models equipped with GM's Super Cruise Level 2 automation capability. But then we added additional sensors to the vehicle platform. So you can see that's where the one of the Valentine lidars installed. This is one of the radars installed behind the bumper. That's the antenna, GPS, and there's a bunch of things in the trunk. But this is a final product. So all the sensors were integrated and try to make it look like a normal vehicles, close to production type of vehicles. Okay. Now this is a hardware architecture for that vehicle. So in total, the sensing part, we have six Valentine 16-channel lidars, and 4 long-range radars installed. Plus, we can have access to the stock vehicles radar. So there are 6 more to be utilized. And then we have 2 cameras plus 1 mobile eye camera. And of course, we need to have connectivity, okay, to make it not just automated, but also connected vehicle. So we have installed a DSRC module on the vehicle. We, at the beginning, we're trying to install a experimental Continental E-Horizon module. But eventually we didn't fully utilize this one, but we just leveraged HMI capability from that thing. Computing power-wise, we have in total 5 CPUs installed. That's a lot of computing resource, but at the same time, it consumes a lot of energy. We have to reroute the AC pipe into the trunk to cool them down. So that's one thing. So we have 2 micro Autobox. One of them we developed as our in-house drive-by-wire system. So because we can have access to all the vehicle cams, so we can bypass for example, steering, brake, acceleration control commands, and directly send those commands from the MAPX to vehicles EPS, EBCM, or to control the secondary actuators such as turn signals, flashlight, headlights, those kind of things. Okay. We also have another dedicated real-time controller to do the powertrain control ECU calibration control. Okay, so that we can recalibrate the ECM and also transmission control. Okay, so overall it's a quite a lot of components integrated and quite a complex system to debug. Okay. So after talking about the hardware, let's take a look at the software design. So basically, we took the software developed by both CMU and GM as a very kind of classical architecture. We have the perception, we have a hierarchical planning from the mission planning or route planning, behavior planning, all the way to short-term path planner, and then goes to the actuation part. So very classical architecture. But on top of that, we basically integrated new algorithm to enable the long horizon speed planning. Okay, leveraging the onboard sensing capability plus the connectivity. So here, the connectivity, we mainly focus on getting signal phase and timing from the connected traffic lights. So that's a focus. Then to enable eco driving for the system. So that includes, for example, if you can predict there's a lot of traffic in front of you, or the traffic light is going to turn red, although right now it's green. You want to actively manage or plan your vehicle's speed trajectory so that you can achieve the most efficient driving. Or departure, you can calibrate the aggressiveness when you start from a stop. And eco cruise, basically, you want to make the speed trajectory of the eco vehicle to be smooth and harmonized with your surrounding traffic. Okay. In order to achieve that, we designed two components. So we introduced a parametric driver model and also conduct a real-time optimization with consideration of several factors, including safety, comfort, fuel consumption, of course. That's a kind of a main thing considered, and also progress. So I'll introduce how the algorithm considers those factors. So this is the parametric driver model we derived from the very classic intelligent driver model. But the difference is now we have to consider, for example, the stop situation. Okay, there are three terms governing the acceleration or the speed profile. Basically, one of the speed tracking. So we have the speed limit of the road as one of the parameters. And of course, we have to look at the car following distance. Okay. The third one is just the stop. Could be a stop sign location, or it could be the distance to a traffic light, a red light. Okay. So this is how you define those minimum distance. Okay. There is one variable here, very critical for our design, is the headway. Okay, so this headway defines the minimum distance for the car following, which is a dynamic part for this equation. There are many parameters we can tune to change the driving behavior derived from this model. For example, we can give different value for the aggression factor. Okay, so if you look at the curves with different aggression factors, it can dramatically change how the vehicle accelerates or decelerates. Okay, the speed factor basically determines whether you will drive at the speed limit or below or above. The headway, of course, it also changes when you have a lead vehicle in front of you. It determines how closely or how far you will drive behind that lead vehicle. Okay, and later on we'll introduce our sample-based method and how to real-time optimize this time gap. Okay, another one is coasting factor. This is basically can calibrate it based on the powertrain characteristics so that we can maximize the fuel saving when we slow down. Oh, by the way, if there's any question anytime, feel free. Happy to answer. So this is our real-time optimization algorithm. So there are several steps. The first one is to assess the Eagle vehicle's current traffic environment. We specifically focus on, for example, what's the status or future status of traffic lights, okay? And also what's the lead vehicle situation. Because mostly if this project focus on longitudinal, we don't do the steering or lateral control because longitudinal plays a major role in terms of the fuel economy. So your headway could be, we set a constraint, could be between 0.5 second or 5 second. Of course, we have the different weighting factors based on the distance we can evaluate. Then we will do the we'll do the sampling for the headway. So assuming your current headway is 1 second, and we predict that we sample in the long horizon 10 to 15 seconds, what would be the options? What would be the candidates? What would be the potential trajectory that the Eagle vehicle can drive at? Okay, for example, we can start this small headway and gradually increase to the maximum, or we can reduce to the minimum, which is 0.5 second. That'll lead that difference of headway will lead to a different speed trajectory or acceleration profile, okay, based on this parametric driver model. Okay, for each headway profile, we'll get a different acceleration profile. Okay, then we can inject that into the model and do the forward simulation. Okay, based on the current Eagle vehicles location dynamics and surrounding vehicle, especially the lead vehicles current status and kinematics model, we can do the prediction, okay? How in the next 10, 15 seconds, how that situation will evolve. Then we'll do the multi-objective cost evaluation for each candidate profile. Pay attention to those 4 factors and then get the most optimal one and do the use that one as to be executed. Okay, so that's the algorithm development. But in order to validate effectiveness, how that affects the fuel economy, we developed 4 different testing approaches to validate. Okay, the first one is large-scale simulation. Second one, in-depth simulation, and vehicle-in-a-loop testing and road testing. Okay. So this part was handled by Unreal mainly. So they took the algorithm we developed and plug into their the database. They actually selected 10,000 routes from their TSDC database and do the synthetic routes and basically longitudinal speed profiles, and then speed out and go through their FASN model and speed out the fuel economy difference. They've done this for 10,000 routes. So from that 10,000 routes, we select roughly 16 to 20 typical routes, and we'll do the in-depth simulation. So we generate those routes in the 3D simulation environment and test with higher fidelity. Okay. In the interest of time, I might need to go a little bit faster. So we construct this co-simulation environment that involves a virtual traffic environment, and of course the autonomous driving software stack, plus the in-house vehicle and propulsion model. Okay, this can closely reflect the dynamics and fuel consumption of the CT6R test vehicle. Okay, and we put them all together to do a co-simulation for those selected scenarios. Okay, so this is just a short video clip to show how it works. So you can see that's the Eagle vehicle's model, and we have traffic lights. The vehicle will predict that traffic light phase and timing, and drive in this virtual scenario. And we can collect the fuel consumption or other vehicle information from the vehicle high fidelity vehicle model. Okay. That's how we do our in-depth simulation. Then we move one step further, because everything before that was simulation. Now we start to really look at how does that apply to real vehicle, right? So we did this vehicle in a loop setup. The idea is similar to the co-simulation. We still use a virtual environment, but this time we'll generate the speed trajectory and directly apply to a real vehicle, the real test vehicle running on the chassis dyno instead of the vehicle model. Okay, of course we have dyno control, and we have the real-time feedback, real-time speed and other measurements goes into a 3D vehicle dynamics model. Okay, and goes back to the virtual environment to close the loop. Okay. So this is the setup we have at the back then at GM Proving Ground. Okay, so the vehicle was secured on the chassis dyno, but in front you can visualize the virtual environment. Okay, the vehicle is being tested in. We also have a fuel meter hooked up to the vehicle. That's one of specific benefit we can get from this vehicle in the loop setup, because we do want to have the precise, that's a kind of a requirement, that we want to have the real-time precise fuel consumption measurement. So in this indoor setting on the chassis dyno, we are able to do that. So this is in the control room. We have the virtual environment simulated, the autonomous driving software, and the controller, okay, and the 3D vehicle dynamics model running at the same time. This is just the cabin view. If you're a driver, or actually if you're a passenger on the driver's seat, this is what you can observe, the virtual environment, but at the same time you can real-time monitor the fuel consumption and other powertrain characteristics. Okay, so this is basically, we can do the cycle-to-cycle comparison to see for each scenario how much cumulative fuel consumption we had. Okay, this is engine map and other calibrations. Okay, and this is a video clip to show how everything is in motion. So you can see secured on the chassis dyno, the vehicle is driving. The dynamics is fed back to the virtual environment. reacting to, for example, the stop sign. Of course, when you do a turn like this, we don't steer the vehicle on the chassis dyno, but we do send the steering command to the 3D vehicle dynamics model to augment that, so that in the 3D environment you still have the left turn, right turn, the lateral dynamics. Okay. Then you will see that this vehicle can interact with other vehicles. You spawn in this virtual environment, um, uh, and also, of course, the traffic lights. Okay. So we would basically kind of create a metaverse for this vehicle to be tested. And of course, after doing the vehicle testing, our next step would be how do we put this in real world testing on the road testing. So one thing we need to again configure is how to get the traffic lights signal, okay, from connected traffic light. So this is what we did. Basically had a instrumented a radar roadside unit, which sending out the SFAz information, and we have this onboard CODA onboard unit integrated to the vehicle and receiving that signal and pass along to the autonomous eco-autonomous driving software stack to synthesize through that parametric driver model, and also goes through the real-time optimization. So we can get the traffic light information incorporated into the driving. So we actually did road testing. Of course, we built two identical vehicles, one for GM, one for CMU. On the CMU side, more focus on the road testing. I'm not sure if Rahul can recognize this route. So this is this is a testing we did with Professor Raj Kumar and other students on a public road with all the equipment kind of integrated functionality. So it was actually during COVID, so you can still see that we're wearing face shields. Feel like centuries ago, but that's what happened back then. Got quite a bit delayed for the testing, but we still managed to get it done, put the vehicle on the road, and collect some results.
And this is running like what kind of software now for the autonomous driving?
So for this part, this is the software stack we built upon the version that GM and CMU co-developed, but we modified it. So we kind of insert our autonomous algorithm into the software stack.
Cool.
So overall, this is a kind of a summary of the energy benefit we achieved from this 4 different testing approaches. So like I mentioned, for the large scale simulation, we had 10,000 different routes. In-depth simulation dramatically goes down to 16. That's kind of 3D environment. It's really time consuming to construct those scenarios. And we selected down to 3. This involves a real vehicle for vehicle in the loop testing. It's even more time consuming and a lot of resource. And we eventually just had 1 route for road testing. Okay, but back then the idea is we try to establish the connection from one step to next. Okay, so that some of the statistical results can be inferred or derived from the previous step. So overall, we got very similar results from different methodologies. So roughly between 11 and 14% of the fuel benefit. Of course, there's separate eco routing benefit from Unreal's simulation that was to choose the most efficient route, just like the currently Google Map offers, right? The eco route. So Google actually collaborated with Unreal. They commercialize this feature. But that's additional roughly 17%. So in total, we achieved about 20% of the target. But that was a lot of testing and validation and the tools development happened. Okay, so that's very quickly about the old project. So now I'm gonna kind of shift the gear a little bit and talking about the project we started from last year. Okay, mainly focus on safety. So first of all, I like to give a kind of an introduction on background, how automated vehicle are going on in Arizona. So Arizona is kind of a first state in the nation to embrace this new technology and allow more flexible testing and even commercialization deployment, especially in the Metro Phoenix area. Okay. So you will see way more robotaxi. Nowadays, you can actually have a map and hail a robotaxi, way more robotaxi in this region. You will see also, for example, GM Cruise was testing in this region before, and this is our vehicle. So 3 vehicles were on display on last year's one of the events. And Arizona is kind of a AV friendly state, not just because of the legislation, also because of the good infrastructure, the weather here. So everyone's embracing the first day of spring. We start to look at the first day of summer already over here. So year-round sunny days, dry weather, not much rain and snow to impair the sensing capability. Okay. So there are dozens of companies are testing here. Okay, so that's kind of an advantage or uniqueness in Arizona. Okay, but the problem is that the public doesn't know the really the safety side of things, even though we have many robotaxis, many autonomous testing fleet running around. So back in 2018, that Uber accident happened near ASU Tempe campus. It was one pedestrian killed by that accident. It's quite a tragedy, but that brings people's attention to how to evaluate, especially in the state of Arizona, how to evaluate safety, how to regulate AV safety. So back then, there was a Institute of Automated Mobility established with both industry and public institution partners participating. Okay. So our project is kind of derived from there, from that institution. So I worked with Dr. Jeff Wishart from Science Foundation Arizona and Arizona Commerce Authority, and he's also affiliated with IAM. Together, we want to develop a safety case-based framework for AV testing evaluation. So this project was kicked off last year. Like I mentioned, currently there's no comprehensive federal level regulation of AVs. Some states have some guidelines regulation, but still it's not comprehensive. So we can see that NHTSA are trying to promote something. They're trying to give out guidelines to build up the safety case concept. They even indicated 3 standards can be utilized, but everything is still in motion, still under development. So FTAP mission we want to try to develop a comprehensive framework can be adopted by either third-party evaluation of AV technology, such as AV regulators, or can be adopted as part of the AV development. Okay. So Dr. Jeff Wishart and other colleagues from IM have spent quite a few years before I joined ASU to develop the metrics for AV safety evaluation. Okay. Actually, Jeff led the SAE on-road automated driving community via a verification and validation task force to develop this SAE J3237, which contains mainly three categories of approach of metrics. Black box, meaning you don't you're observing the vehicle's behavior from outside, right? Gray box, you are able to interact with the system and get some numbers and metrics from that. And white box, assuming that we have access to all of data or most of the important data from the vehicle itself to come up with some metrics. Okay. Not just those metrics, we have proposed or developed the kind of a concept to aggregate those metrics for example, for certain scenarios, there might be several metrics, safety envelope violation, traffic law, collision incident, those kind of things. You can aggregate those metrics and come up with a single score for that particular vehicle in that particular scenario. Okay, so this is a concept that's been published in this SAE paper to summarize how this score can be calculated. So the idea is we're trying to propose a driver test, right, for autonomous system, just like a driver test for human driver. Eventually, you have to give a score, pass or fail at least, to that driving scenario, to that driver. So that was kind of the concept behind this. Okay, so this DA scores approach has been validated extensively in simulation, but with our lab participating, we are able to now move forward to some real-world testing, leveraging the research vehicle. Okay. Of course, the idea is the pilot study will be done on our research vehicle, and then the learning and the framework can be transferred to, for example, the industry partner we're working with, May Mobility, to their fleet and to do further validation. Okay. At the same time, we will leverage the previous study. We have a smart drive intersection instrumented, so we can still leverage the black box approach to analyze the testing results. So a little bit about our new vehicle. So we built this research platform on top of a pure electric. It's a Mazda Marquis pure electric vehicle. It has a Blue Cruise level 2 automation. We augmented the sensing by adding 2 more Ulster LiDARs, 1 RGB camera, although we are in the process of adding multiple more, and high precision GPS system. And again, a lot of computing power and controllers in the trunk. We also have a long range radar installed in the front. So that's our kind of a vehicle setup. And now comes Autoware. So we are able to leveraging the open source community, all the contribution from the audience, to integrate this to our test vehicle. Okay. Of course, one thing we have to do by ourselves is that we're integrating Autoware.universe with data speed drive-by-wire system, but there's no existing vehicle interface out there. So we have to develop our own interface to basically translate the Autoware's control signals to the data speed drive-by-wire system, so that those two pieces can be working together. So we have done this development work, and also the since it's we couldn't find it the open source interface, we made it available. So you can find the GitHub link from this paper. Will soon come out in this year's SAE World Congress. Okay. Then after all the integration, we start the road testing just around our campus route. So this is the end of last year. We're doing some road testing with our students. Okay, so but once we finish the vehicle integration and start the road testing, we kind of we face an issue is that in simulation, we can arbitrarily design things and do the testing. We can arbitrarily design corner case, very complex scenario. But in real traffic, you cannot dictate, right? So then we come up with this idea to develop the road testing with digital twin and augmented reality. Okay, so the idea is basically, of course, we have the our ego vehicle running in the physical world, right? We have to interact with other traffic, other vehicles or pedestrians. But at the same time, can we integrate the digital part, the simulation part? If we do some simulation, can we directly replicate it in the real world road testing, right? Can we put the virtual vehicles and virtual pedestrian and overlay with the physical world and have the vehicle test out the planning and control capability, right? So this is kind of a original concept and design, and that's kind of the next tool we developed for the testing. So first of all, we developed the digital twin for our vehicle. So we got the 3D model and we calibrate the dynamics. We configure the sensor so that the sensing capability is close to the real vehicle. And we develop policy to synchronize this digital twin with our real vehicle. And of course, we again developed a virtual test ground for our campus route. So basically, this is a ground truth, and this is our digital replica of the campus route. Okay. Then we create the interface between Kala simulator and Autoware. So basically, we extract those virtual objects from Kala and publish to a topic that can be accessed by Autoware perception and planning module. And then to close the loop, we send the real-time, the real vehicle's coordinates back to the localization module to spawn our ego vehicle and track the synchronize ego vehicle's motion in the virtual environment. Okay, so this is very quickly to show you how this works. So our vehicle is parked on the campus on the road. But you can see the red box, that's a virtual object injected by the simulator. But at the same time, you can see we're still detecting the real vehicles, the shuttle, the car. And again, there is a virtual car from Kala that's being detected. So that's kind of a mixed reality for vehicles perception module. Then we also test out when the vehicle is in motion. Okay, so this is a very simple scenario we can create. So we have a few vehicles in front of us. We can test out the car following maneuver. In real world, there's just empty road. but over here we have a traffic so that we can interact. The vehicle will slow down and follow that vehicle of virtual vehicles. So it's a relatively safer to hit this one than the real ones on the road. Okay. So we have done so far 1 year into the project, we have done a lot of tools development capability to enhance our testing capability. So future work for this AppTab project is to really put this tools into testing and validation. So you can see we have collaborated with Science Foundation Arizona. There's quite a lot of activities already, especially from the simulation side and the methodology and design methods development. But in the future, there's a lot of validation work will be conducted, and those tools will be utilized to support this validation. Okay. So this slide is trying to summarize some of the AV regulation challenges, although we develop all kinds of tools, but still, currently there's no agreed upon AV verification and validation process, right? Each AV developer use their own proprietary method, and there's no agreed upon set of scenarios. Okay, we can create typical scenarios, but there's no existing standards set, just like the FTP for fuel economy testing or other standard crash testing, those kind of things. Another challenge is the AV data, right? For our research vehicle, we can have a white box, it's a complete open source, but for industry partners, for industry AV developers, they might not be willing to share some of the data, right? Unless we kind of specifically list out this signal or other signal is important, has to be there. And there are different SAE levels. Each different level might have different specific process approach to regulate, to validate. Also over-the-air updates, right? You're testing, evaluating the vehicle today, and next day, there's another patch, right? The software is different. And also AI-based system, right? That can sometimes is not transparent, difficult to evaluate, and sometimes they can learn the evaluation process and optimize just against that. Okay, so that's some kind of challenges. But again, so for the first year, we focus on developing the tools for evaluation and testing, and a lot of students were involved and made contribution to those tools. One more tool is our driving simulator. So it's with a motion base that student has developed. So eventually this one will be also connected to the vehicle and to our Autoware package. Okay. But they're also having a lot of fun. I think sometimes they just use this to play a video game, racing game. Okay. So final thoughts. I think the safety assurance case definitely needs to be built through a comprehensive combination of evidence, right, from various methods. We can do the simulation, vehicle in the loop, on-road testing, closed track testing, and maybe other things. Maybe just focus on the perception part using AI to evaluate, but has to be a comprehensive combination of methods. And we know that many other organizations and consortium are working on this, and hopefully our effort will be part of that and to make contribution. So final word is from my collaborator, Jeff Wishart. He said, collaboration is a new competitive advantage. Okay. And I hope and look forward to the potential collaboration from this community as well. Yeah. So that is all the slides I have for today. Thanks for your time and attention.
Thank you so much, Junfeng. This was a great talk. And I'll open now the forum for any questions from the audience.
I have a quick question. This is Khan Azbey. I mean, great talk. Thank you very much for taking time. So this mixed reality environment, so you are injecting virtual vehicles into the real world environment, if I understand correctly.
Yeah.
But the driver in the real car, do they get confused? Because I mean, you have real vehicles. I mean, I got confused. Maybe it's my age, whatever. And then you have this virtual vehicles, and also, I mean, after a while, they learn that virtual vehicles are only virtual vehicles, so they might be less careful. But that's not that important. I think this kind of differentiation between real vehicles and virtual vehicles. How does it work? Did you
Yeah,
have?
yeah, absolutely. You're right. When I was sitting on the driver's seat, I got confused too. There are two monitors. One is you can look through the windshield, look at the real thing, but there's a monitor to show you the virtual vehicle. But the real idea behind this is to let the autonomous system to assess both real and virtual objects.
I
So
see.
autonomous system has no issue with combining both and interacting with both.
Right. So this is
So
completely autonomous. So there's no driver involvement in that. Just
right. So we're driving hands-free.
I
So
see.
we're just observing what's going on. Absolutely, it's a little bit confusing to human eyes.
Yeah. Yeah. All right. Okay. Good.
Yeah,
Thank you.
yeah,
Hi, this is Zhao. Can you hear me?
yeah. I can hear you, Charlie.
Hi, thank you, Junfeng, for this wonderful talk. So follow up the previous question. This virtual injection, I wonder this simulation, was it running on the vehicle stack or it is somewhere on the server and then the injection is done through, I don't know, maybe through the internet or some communication, or it is real time with the vehicle?
Yeah, that's a great question. So right now it's on board of the vehicle. So we have two computers, right? One computer is running Autoware. The other computer is running using Color Simulator. So both are connected. Those two computers are connected through Ethernet switch, communicating with each other. But you're right. Actually, in our plan is that potentially we can do the wireless communication. Okay, so you can remotely inject or create virtual scenarios if needed.
Okay, yeah, thank you. Because at UB we had similar ideas. Maybe I can follow up with you privately to have some discussions. Very interesting work and very relevant to our work too. Thank you very much.
Yeah, absolutely. Thanks.
Hello, Professor. This is Sugosh Rao from Transportation Research Center. Thank you for the talk. It was really exciting to hear. Another question about the virtual object injection. So, are you guys just updating the object list in the ROS node, or is there any aspect of sensor in the loop? Is it like, are you feeding actual camera feed from Carla into your cameras, or is it just the object list that's being updated?
Yeah, good question. Right now, it's just object list. Because if we are going to inject the raw image or even raw point cloud data back to Kala, there are a lot of other issues we have to consider. For example, even though we build the virtual test ground, it's trying our best to simulate the environment. It's not identical. There will be a lot of confusion caused by the perception part. So right now we just focus on extracting the object list from Color Simulator and directly put that into Autoware.
All right. I'd also thank you for publishing your bridge between Autoware and data speed. We are currently running Autoware.ai with data speed drive-by-wire, but we want to update to Autoware.universe. And since you've done the groundwork, that's going to help us quite a bit. Thank you so much.
Yeah, glad to know. I think that's definitely our intention, to get an open source, because we struggled in the beginning because there's no such interface out there. We do benefit from a lot of open source component from Autoware, and we want to contribute back to the community by put our effort out there. But if you need any support or any help with that vehicle interface or with your vehicle's integration, I can have my student to be there and provide some kind of tips or insight.
But thank you so much. We will probably take you up on that.
Yeah.
Wonderful. I think there's a lot of excitement in building up on extending all the hard work you've done, Junfeng. And I think there's going to be a lot more with infrastructure-based support along with Autoware extending to that. And I feel we will have a lot more collaboration opportunities coming through. I'll also follow up with you offline.
Yeah, absolutely. Absolutely. Look forward to it.
Thank you. Thank you so much for this wonderful presentation. I learned a lot. And thank you everyone for joining us today. And I hope you have a good rest of your day.
Yeah. Thanks.
Thank you.
Take
Bye.
care, everyone. Yeah. Bye, Rahul. Thank you.